close your eyes for a moment and imagine absolute darkness. Not the darkness of a moonless night, but the darkness before light itself existed. Now imagine that darkness beginning to stir, to collapse inward, to heat and glow and finally explode into brilliance. This is not a metaphor. This is happening right now in distant corners of our galaxy, trillions of kilometers away, in clouds so vast they dwarf our entire solar system. New stars are being born in a process so patient and profound it can take millions of years. Tonight, you and I will witness this journey together from the very beginning. Our journey begins in a place that might seem like nothing at all. Molecular cloud drifting through the spiral arms of the Milky Way. From Earth, if you could even see it, this cloud would appear as a dark patch against the stars, a void where light cannot reach. But this is not emptiness. This is potential. Within this darkness, hydrogen and helium molecules float in the cold, their temperature hovering just above absolute zero. Dust grains no larger than particles of smoke drift alongside them. This cloud is ancient, perhaps tens of millions of years old, and it has been waiting for the right moment, waiting for the spark that will transform it from darkness into light. These stellar nurseries are among the largest structures in the galaxy. A single molecular cloud can span hundreds of light years from edge to edge and contain enough material to birth thousands of stars. Imagine a volume of space so vast that light itself would take centuries to cross it, filled with gas so thin that it makes the best vacuum on Earth seem dense by comparison. Yet within this near emptiness lies everything needed to forge a sun. The hydrogen that will fuel nuclear reactions, the heavier elements scattered by dying stars long ago, the dust that will someday coalesce into planets. All of it floating, waiting in the cosmic dark. What transforms these peaceful clouds into stellar forges? Sometimes it is the shockwave from a nearby supernova, the death cry of a massive star rippling through space at thousands of kilometers per second. Other times it is the gravitational influence of the galaxy itself, compressing the cloud as it orbits through the spiral arms. Or perhaps it is simply the random collision of two clouds passing in the night, their combined mass reaching a critical threshold. Whatever the trigger, once the process begins, it cannot be stopped. Gravity, that patient and inexorable force, begins to pull the cloud inward. The birth has begun. Let us pause here and consider what we mean by collapse. This is not a violent event, not an explosion in reverse. It is gentle, almost tender. Individual gas molecules begin to drift together, drawn by the almost imperceptible gravitational pull of their neighbors. At first, the movement is so slow that if you could watch it in real time, you would see nothing change in a human lifetime. Atoms drift inward at speeds measured in meters per second across distances measured in light years. This is the universe working on its own timescale, a timescale where a million years is but a moment. And yet this slow dance will culminate in one of the most energetic events in nature. The temperature in the cloud is almost unimaginably cold. We are talking about temperatures around 10 degrees above absolute zero, where even molecules barely have the energy to move. At these temperatures, atoms cling together, forming simple molecules like hydrogen gas and water ice. The darkness here is absolute. No light penetrates the dense core of the cloud. No warmth reaches these innermost regions. This is the coldest, darkest place in the galaxy. And yet, it is also the birthplace of light itself. Can you feel the profound irony in that? The brightest objects in the universe beginning their existence in the deepest cold and darkness imaginable. As gravity continues its patient work, small irregularities in the cloud begin to matter. A region slightly denser than its surroundings pulls in more material, becoming denser still. This creates a feedback loop. More mass means stronger gravity, which pulls in even more mass, which strengthens gravity further. Slowly, over tens of thousands of years, distinct knots begin to form within the cloud. Each knot is a seed, a place where a star might one day shine. Some of these seeds will grow. Others will be torn apart by turbulence or disrupted by their neighbors. But the successful ones, the ones that gather enough mass and survive the chaos, they will become something extraordinary. Imagine you could speed up time and watch this process unfold like a time-lapse film. You would see the cloud begin to fragment, breaking apart into smaller clumps. Each clump rotates slowly, a remnant of the original motion of the cloud. As material falls inward, this rotation speeds up, just as a figure skater spins faster when pulling in their arms. The clump begins to flatten, forming a disc with a dense bulge at the center. This is no longer just a collapsing cloud. This is the beginning of a solar system. The dense center will become a star. The disk around it holds the raw material for planets, moons, and perhaps even life. At this stage, we can begin to call it by a new name. This is no longer just a collapsing cloud. This is a protostar. The word itself carries a sense of promise and potential. Not yet a star, but something that will become one. The core is still dark and cold by stellar standards, but compared to the surrounding cloud, it is a furnace. The temperature has risen from 10 degrees above absolute zero to perhaps a few thousand degrees. Matter continues to rain down from above, adding mass and energy to the growing core. With each passing century, the protostar grows brighter, hotter, denser. The transformation has truly begun. Deep within the growing protostar, something remarkable is happening. As more and more matter falls onto the core, the pressure at the center increases. And with pressure comes heat. This is not heat from any chemical reaction or nuclear process yet. This is heat from pure gravitational compression. Every atom that falls inward converts its gravitational potential energy into kinetic energy, into motion, into heat. The core temperature rises from thousands to tens of thousands of degrees. The darkness begins to give way to a deep red glow. If you could somehow stand at a safe distance and look toward this hidden core, you would see nothing yet. The thick cocoon of dust still blocks all visible light. But in infrared, the protostar is beginning to shine. The process of collapse continues for hundreds of thousands of years. To the protostar, this is its entire existence so far. But to the universe, it is barely a breath. During this time, the protostar feeds constantly. Gas from the surrounding disk spirals inward, following magnetic field lines that thread through the cloud. Some of this material reaches the surface of the protostar and merges with it, adding to its mass. But not all of the infalling material reaches the surface. Some of it is caught up in powerful magnetic fields and redirected. It is funneled toward the poles of the rotating protostar, where it is ejected back into space in twin jets of superheated gas. These jets are among the most beautiful and dramatic structures in astronomy. They can extend for light years, plowing through the surrounding cloud at supersonic speeds. Where the jet impacts the ambient gas, it creates glowing shock waves called Herbig-Haro objects, brilliant knots of light that mark the protostar's presence. These jets serve a critical purpose. They carry away excess angular momentum, allowing more material to fall onto the protostar. Without them, the rotation would spin up so fast that infalling material would be flung back out before it could join the growing star. The jets are the release valves that allow the birth to continue. As we watch this cosmic drama unfold, we might ask ourselves what determines the fate of a protostar. Will it become a star like our Sun, burning steadily for billions of years? Or will it become a massive giant, living fast and dying young in a supernova? The answer lies in how much mass the protostar can gather before the cloud around it is depleted or blown away. The feeding frenzy cannot last forever. Eventually, the protostar will become bright and hot enough to begin pushing back against the infalling gas. But for now, in this early stage, it is still growing. Every year, it adds the mass of Jupiter or more to its bulk. Every year, its core grows denser and hotter. The disk of material surrounding the protostar is a world unto itself. This disk will eventually give birth to a planetary system, but right now it is a chaotic place. Gas and dust orbit at different speeds depending on their distance from the center. Closer in, the material moves faster, heated to thousands of degrees by the nearby protostar. Further out, the disk is cold and dark, with temperatures approaching those of the original cloud. Turbulence and magnetic fields churn the disk constantly. Spiral density waves propagate through it like ripples on a pond. And within this maelstrom, tiny dust grains are beginning to stick together, forming the first pebbles that will one day grow into planets. Let us take a moment to appreciate the sheer patience of this process. From the outside, if you could watch this protostar for a human lifetime, you would see almost no change. The disk would appear frozen. The jets would seem stationary. Only the most sensitive instruments would detect the slow brightening, the gradual increase in temperature. But we have the privilege of a God's eye view, of seeing time compressed. And from this perspective, we can watch the inexorable march towards stellar birth. The protostar is now perhaps 500,000 years old. It has gathered a significant fraction of a solar mass. Its core temperature has reached 1,000,000 degrees. But it still has a long way to go. Within the core, atoms are colliding with ever-increasing violence. The pressure is now millions of times greater than the pressure at the center of the Earth. The temperature, while not yet hot enough for fusion, is high enough to strip electrons away from atoms, creating a plasma of bare nuclei and free electrons. This plasma is opaque to light. Photons born in the core scatter off the plasma countless times, taking thousands of years to random walk their way to the surface. The energy generated by gravitational collapse is trapped, building up, waiting. The core is like a battery slowly charging. And when it is finally full, when the conditions are finally right, that energy will be released in a new form. Here, nuclear fire. We are now approaching a critical threshold. The protostar has accumulated roughly half the mass it will eventually have as a main sequence star. Its core temperature has climbed to several million degrees. At these temperatures, a new process begins. Deuterium, a rare form of hydrogen with an extra neutron, begins to fuse with ordinary hydrogen. This is not yet the main fusion process that will power the star for billions of years. Deuterium fusion is merely a preview, a warm-up act. Light, but it is significant. For the first time, the protostar is generating energy through nuclear reactions. For the first time, it is sustaining itself not just through gravitational collapse, but through the fundamental force that binds atomic nuclei together. It is taking its first steps toward true stardom. The protostar is now what astronomers call a T Tauri star, named after the first example discovered in the constellation Taurus. These are tempestuous young stars, variable and energetic. The surface is mottled with enormous star spots that dwarf any sunspot ever seen on our sun. Powerful flares erupt from the surface, releasing as much energy in a few hours as our sun emits in an entire year. The stellar wind, a stream of charged particles flowing away from the star, is thousands of times stronger than the solar wind we experience in our own system. This is a star in adolescence, wild and unpredictable, not yet settled into the calm routine of middle age. The disk surrounding the young star is also evolving. The inner regions have become so hot that any dust grains have vaporized, leaving only gas. Further out, the dust survives, and it is here that the real work of planet formation begins. Dust grains collide and stick together through electrostatic forces. Pebbles grow into boulders, boulders into planetesimals. These planetesimals, objects the size of mountains or even small moons, have enough gravity to begin pulling in more material. The largest ones grow faster, sweeping up everything in their orbital path. We are watching the seeds of planets take root. Some will grow into massive gas giants. Others will remain small and rocky. All of them are being forged in this crucible of heat and chaos. Back in the stellar core, the conditions continue to intensify. More mass is still falling onto the star from the disk, though at a slower rate than before. The core temperature has now climbed past 10 million degrees. At these temperatures, ordinary hydrogen atoms have enough energy to overcome the electromagnetic repulsion between their positively charged nuclei. They can get close enough for the strong nuclear force to take hold, close enough to fuse. But this is not yet a sustained reaction. The core is not quite dense enough, not quite hot enough for stable hydrogen fusion. These are sporadic events, brief flashes in the dark. The star is knocking on the door of true ignition, but it has not yet been answered. As the star continues to contract, an interesting balance begins to emerge. Gravity is still trying to compress the core further, but now there is resistance. The pressure from the hot plasma pushes back against gravity. For the first time in the star's life, these two forces are approaching equilibrium. When they finally balance perfectly, the star will stop contracting. It will reach what is called hydrostatic equilibrium, where the inward pull of gravity is exactly matched by the outward push of pressure. This balance is delicate and dynamic, will define the star's structure for the rest of its life. But we are not quite there yet. The core must get a little hotter still, a little denser, a little closer to the critical threshold. The protostar is now about 1 million years old, though the exact timeline depends on its mass. More massive stars evolve faster, racing through their formative stages in perhaps 100,000 years. Less massive stars take their time, spending 10 million years or more in this pre-main sequence phase. Our star, similar in mass to the Sun, is somewhere in the middle. It has been visible as an infrared source for most of its life, but now it is finally beginning to shine in visible light. The cocoon of dust has thinned. The optical light from the stellar surface can escape. If there were eyes to see it, this young star would appear as a brilliant ruby, glowing deep red-orange in the darkness of the nursery. The stellar wind and radiation from the young star are now strong enough to begin clearing away the surrounding gas. The wind pushes outward, creating a bubble of hot, ionized gas around the star. At the edge of this bubble, where the wind collides with the cooler molecular cloud, a shock wave forms. This shock heats the gas, causing it to glow. The young star is carving out a cavity in its birth cloud, creating its own space in the cosmos. Eventually, all the nearby gas will be dispersed. The star will emerge fully from the nebula, standing alone with only its planetary system for company. But that process will take another few million years. For now, the star is still connected to its origins, still surrounded by the cloud that gave it birth. Let us pause and reflect on where we are in this journey. We began with a dark, cold cloud. We watched as gravity gathered that cloud into a dense core. We saw the core heat and glow, becoming a protostar. We witnessed the formation of a disk and the first stirrings of planet formation. We watched the protostar grow and evolve, fueled by gravitational contraction and the burning of deuterium. And now we stand at the threshold of the most important moment in the star's life. Everything that has happened so far has been a preparation, a long, patient build-up. The core temperature is approaching 15 million degrees. The density is climbing toward values 100 times the density of water. The conditions are almost perfect. The moment of true stellar birth is at hand. What exactly is about to happen? In the core of the protostar, hydrogen nuclei are colliding billions upon billions of times every second. Most of these collisions result in nothing more than a bounce, the nuclei flying apart again. But occasionally, very occasionally, two hydrogen nuclei collide with such speed and precision that they overcome their mutual repulsion and fuse together. In that instant, a tiny amount of mass is converted into energy according to Einstein's famous equation. That energy is released as gamma rays and neutrinos. The gamma rays heat the surrounding plasma. The neutrinos escape into space, carrying news of the fusion event to the cosmos. And with each successful fusion, the core gets a tiny bit hotter, making the next fusion a tiny bit more likely. A chain reaction is about to begin. The core temperature has reached 15 million degrees. The density is 150 times that of water. These are the magic numbers, the conditions required for sustained hydrogen fusion. The rate of fusion reactions is now accelerating exponentially. More fusions mean more heat. More heat means faster moving particles. Faster particles mean more energetic collisions and even more fusions. This is a runaway process, but it is not a bomb. The star's immense gravity holds everything in check. The energy released by fusion increases the pressure, which pushes back against gravity. And in a beautiful cosmic dance, these forces settle into a new equilibrium. The star stops contracting. For the first time in its million-year life, it has found stability. It has ignited. This moment, this transition from protostar to true star, is called reaching the main sequence. It is the single most important moment in the life of any star. From this point forward, the star will spend the vast majority of its existence fusing hydrogen into helium in its core. For a star like our Sun, this phase will last 10 billion years. For more massive stars, it might last only a few million. For less massive stars, it could continue for trillions of years, longer than the current age of the universe. But regardless of the duration, this is the star's prime of life. This is what it was born to do. This is its purpose in the grand cosmic scheme. What is happening in the core now? Through a process called the proton-proton chain, 4 hydrogen nuclei are being combined to create one helium nucleus. In this process, about 0.7% of the mass is converted directly into energy. That might sound like a tiny percentage, but remember we are talking about stellar masses. Every second, in the core of a sun-like star, roughly 600 million tons of hydrogen are fused into helium. 4 million tons of matter are converted into pure energy. That energy, in the form of gamma rays, begins a long journey from the core to the surface. It will take 100,000 years for a single photon of light to random walk its way from the core to the surface, where it will finally escape into space. The energy generated in the core must somehow make its way to the surface. In the deep interior, the plasma is so dense that energy can only move through radiation, through photons bouncing from atom to atom. But further out, where the density is lower, a new process takes over. Action. Hot plasma rises toward the surface, cools, and then sinks back down. This creates enormous convection cells, vast circulating rivers of plasma carrying energy from below. On the surface, we can see the tops of these convection cells as granules, bright regions where hot plasma wells up, surrounded by darker lanes where cooler plasma sinks. It is a boiling, roiling surface, but from space it appears smooth and serene, a perfect sphere of golden light. The surface temperature of our newborn star has stabilized at around 6,000 degrees. At this temperature, the star emits most of its light in the visible spectrum, with a peak in the yellow-green range. This is why stars like our Sun appear yellow-white to our eyes. The surface is called the photosphere, the layer from which photons can finally escape into space after their 100,000-year journey from the core. Above the photosphere lies the chromosphere, a thin layer of lower-density gas, and beyond that, the corona, a super-hot outer atmosphere where temperatures paradoxically climb back up to millions of degrees. But from a distance, all we see is the photosphere, that brilliant surface glowing with the light of nuclear fusion. The star is now pumping out an enormous amount of energy. A sun-like star radiates roughly 400 trillion watts of power. That is more than all of humanity has ever generated combined, released every single second. This energy flows out in all directions, spreading across the cosmos. A tiny fraction of it will warm and illuminate any planets that are formed in the disk. An even tinier fraction will escape the star system entirely, becoming part of the background light of the galaxy. And perhaps, billions of years from now, an infinitesimally small portion of that light will fall upon the retina of an observer gazing up at the night sky, wondering about the universe and their place in it. The stellar wind has now reached its mature configuration. Charged particles, mostly electrons and protons, stream away from the star's surface at speeds of hundreds of kilometers per second. This wind carries angular momentum away from the star, slowly spinning it down over millions of years. It also carries the star's magnetic field, stretching it out into interplanetary space. Any planets in the system will live within this bubble of stellar influence, this heliosphere. They will be buffeted by the wind, shielded from galactic cosmic rays, and bathed in the star's magnetic field. The star has become more than just a source of light and heat. It has created an environment, a domain of influence extending billions of kilometers into space. Let us take a step back and marvel at what we have witnessed. From a cold, dark cloud to a brilliant, self-sustaining star, from near absolute zero to 15 million degrees, from a diffuse collection of atoms spread across light years to a compact sphere where fusion transforms matter into energy. This process, this transformation, is one of the fundamental creative acts of the universe. Without it, there would be no stars. Without stars, there would be no heavy elements. Without heavy elements, there would be no planets, no water, no life. Every atom in your body heavier than hydrogen was forged in the heart of a star. You are made of star stuff. Now you have seen how that stuff came to be. The star has ignited, but its work is far from finished. The disk of material that surrounds it is still evolving, still forming the planetary system that will orbit this star for billions of years. The inner regions of the disk are now extremely hot, with temperatures exceeding 1,000 degrees. Only materials with very high melting points can survive here. Metals like iron, rocky minerals like silicates. The volatile compounds, water ice and methane and ammonia, have been driven out to the cooler outer regions. This temperature gradient will determine what kinds of planets form where. Close in, we will get small, rocky worlds. Further out, we will find massive gas giants surrounded by icy moons. Within the disk, the process of planet formation is accelerating. The largest planetesimals have grown into embryonic planets, objects with enough gravity to gravitationally scatter smaller bodies. These embryos clear out their orbital zones, sweeping up everything nearby. Occasionally, two embryos collide in a cataclysmic impact that melts both bodies and merges them into a larger planet. The disk is becoming a shooting gallery, with collisions happening constantly. Some of these impacts will be the last major collision a planet experiences, the event that sets its final mass and composition. One such collision, billions of years in the future, will tilt Uranus on its side. Another will create the Earth's moon. The star's light and wind are now actively sculpting the disk. Close to the star, the intense ultraviolet radiation heats the surface of the disk, creating a photoevaporative wind that carries gas away from the system. This wind limits how long the disk can survive. Gas giant planets must form quickly, within a few million years, before all the gas is dispersed. Rocky planets can take longer, up to 100 million years, since they do not require gas to form. Clock is ticking. The disk's days are numbered. Any planets that have not yet formed will lose their chance. The raw materials will be blown away into interstellar space, scattered and lost. Among the chaos and violence of planet formation, something extraordinary is happening in one particular region of the disk. At a distance of roughly 150 million kilometers from the star, in a zone that is neither too hot nor too cold, a rocky planet is forming. Its orbit is nearly circular. Its size is just right, large enough to hold an atmosphere, but not so large that it traps hydrogen and becomes a gas giant. This planet will eventually become a blue marble, covered mostly in liquid water, with continents and oceans and an atmosphere rich in nitrogen and oxygen. But that is billions of years in the future. For now, it is just a bowl of molten rock, glowing red in the darkness, slowly cooling as it orbits its young star. Further out in the disk, beyond the ice line where water can condense, the conditions are very different. Here, there is more solid material available, and the planetesimals can grow much larger before running out of building blocks. When one of these icy embryos reaches about 10 times the mass of Earth, something remarkable happens. Its gravity becomes strong enough to pull in hydrogen and helium directly from the disk. The embryo rapidly accretes a massive gaseous envelope. Within perhaps 100,000 years, it grows from an Earth-sized icy core to a Jupiter-sized gas giant. This is how the solar system's outer giants formed. This is why they are so much more massive than the inner rocky planets. The newborn star is now a few million years old. Its luminosity has stabilized. Its surface temperature is steady. It has settled into the long, quiet phase of hydrogen burning that will last for billions of years. But the system around it is still dynamic. Planets are still forming, still colliding, still migrating inward and outward under mutual gravitational influences. The disk is thinning as gas is accreted onto planets or blown away by the stellar wind. Within another 10 million years, the disk will be gone entirely, leaving behind a mature planetary system. But for now, the system is still an adolescent, still finding its final configuration, still settling into the architecture that will define it for eons to come. During this turbulent period, the inner rocky planets are being bombarded by leftover planetesimals that have been perturbed from their original orbits. This is called the late heavy bombardment. For hundreds of millions of years, impacts will pummel the inner planets, delivering water, organic molecules, and other volatile compounds. Some of these impacts will be catastrophic, melting the entire surface. Others will be gentler, adding to the planet's inventory of life-giving ingredients. One planet in particular, that Earth-like world in the habitable zone, will receive just the right amount of water and carbon. And on its surface, protected by a magnetic field and warmed by the star, liquid water will pool. Oceans will form. And in those oceans, given enough time, chemistry will become biology. But we are getting ahead of ourselves. That story, the story of life, is a tale for another time. For now, our focus is on the star itself, which has completed its birth and is now entering the prime of its existence. It will burn steadily for billions of years, a beacon of light and heat in the cosmic darkness. It will watch over its planetary family as they evolve and change. It will provide the energy that drives weather and climate, that powers the chemistry of life, that makes worlds habitable. And all the while, deep in its core, it will continue the patient work of fusing hydrogen into helium, converting mass into energy, shining with the light of nuclear fire. We have reached the end of our star's birth, but in a larger sense, we are at the beginning of its story. The main sequence is not just a phase. It is the dominant phase, the phase where stars spend most of their existence. Our star, similar in mass to the Sun, will remain on the main sequence for about 10 billion years. During this time, it will be remarkably stable. Its luminosity might vary by a few percent over centuries, but on average, it will shine with a nearly constant brightness. This stability is the key to its success. This stability is what allows planets to develop atmospheres, oceans, and potentially life. A star must burn steadily for life to have time to arise, but nothing lasts forever, not even stars. As our star fuses hydrogen in its core, it slowly converts that hydrogen into helium. The helium ash accumulates at the center, where the temperature and pressure are highest. Over billions of years, the core becomes increasingly helium-rich, while the surrounding layers remain hydrogen-rich. This changes the structure of the star. The helium core, unable to fuse at these temperatures, is supported only by thermal pressure. As more helium accumulates, the core contracts slightly. This contraction releases gravitational energy, heating the hydrogen shell around the core. And paradoxically, the star becomes slightly brighter over time. The Sun today is about 30% brighter than it was when it first ignited 4.5 billion years ago. This gradual brightening has profound consequences for any planets in the habitable zone. A planet that is comfortably warm today might become a scorching hothouse in a few billion years. Conversely, a planet that is too cold today might become habitable later. The habitable zone moves outward as the star ages. This is the cosmic equivalent of climate change, happening on timescales of billions of years. For life to survive, it must adapt to these changes. It must evolve mechanisms to regulate its environment, to maintain habitability even as the star's output increases. Or it must migrate, spreading to new worlds as old ones become uninhabitable. While the star burns steadily, it is not entirely inactive. Its surface is constantly changing, driven by the turbulent convection below. Sunspots appear and disappear in roughly an 11-year cycle as the star's magnetic field twists and tangles and reconnects. Solar flares and coronal mass ejections erupt sporadically, sending bursts of radiation and charged particles streaming into space. These events can affect the planets, triggering auroras, disrupting magnetic fields, even stripping away atmospheric gases from worlds that lack protective magnetospheres. The star is a living, breathing entity, not a static ball of gas. Its activity waxes and wanes, creating a dynamic environment for its planetary system. Let us take a moment to consider what it means for a star to be stable. The balance between gravity and pressure that we discussed earlier is not static. It is dynamic. If fusion produces too much energy, the core heats up and expands, which cools it down and slows the fusion rate. If fusion produces too little energy, the core cools and contracts, which heats it up and speeds the fusion rate. This negative feedback loop is what keeps the star stable. It is a thermostat, constantly adjusting the fusion rate to maintain equilibrium. Without this feedback, stars would oscillate wildly or even explode. The universe would be a very different and far less hospitable place. As we approach the midpoint of the star's main sequence lifetime, let us reflect on the journey we have taken. We started with a dark cloud and watched it collapse under its own gravity. We saw the formation of a protostar and the disk that surrounds it. We witnessed the birth of planets in that disk. We observed the moment of stellar ignition and the settling into main sequence stability. And now, we are looking at a mature star in the prime of its life, steadily converting hydrogen into helium, providing light and warmth to its planetary family. This is the natural history of a star, a story billions of years in the making, a story that is being repeated countless times across the universe right now. But our star will not remain on the main sequence forever. In about 5 billion years, it will exhaust the hydrogen in its core. When that happens, the core will no longer be able to generate energy through fusion. It will begin to contract under its own gravity, heating up as it does so. This heat will ignite a shell of hydrogen surrounding the inert helium core, and this shell will burn even hotter than the original core did. The additional energy will cause the outer layers of the star to expand dramatically. Our star will swell into a red giant, growing so large that it will engulf the inner planets, perhaps even the Earth. But that is a story for the distant future. For now, our star burns peacefully, a yellow beacon in the cosmos. The birth of a star is not just a physical process. It is a creation event, a moment when the universe brings forth new light from darkness. Every star that forms is an island of negentropy in the vast sea of cosmic entropy, a place where energy flows and structures emerge. Every star that ignites pushes back against the heat death of the universe, if only for a time. And every star that forms seeds. Stars are not just objects to admire. They are the engines of cosmic evolution, the creators of complexity, the forgers of the elements. Without them, the universe would be a cold, dark, lifeless place. With them, it is a cosmos full of beauty, wonder, and possibility. Our star did not form in isolation. Most stars are born in groups, in clusters that can contain hundreds or even thousands of siblings. These stellar nurseries are vast complexes of gas and dust, often spanning hundreds of light years. Within them, multiple regions collapse simultaneously, creating a burst of star formation. For a few million years, the nursery is crowded with newborn stars, all jostling for space, all competing for the remaining gas. Some of these stars will remain gravitationally bound to each other, forming open clusters that persist for hundreds of millions of years. Others will drift apart, scattered by gravitational interactions and the rotation of the galaxy. The most massive stars in these clusters have an outsized influence on their surroundings. These giants, with masses 10 or even 100 times that of the Sun, burn their fuel at a prodigious rate. They are incredibly bright and incredibly hot, pouring out ultraviolet radiation that ionizes the surrounding gas. This ionized gas glows, creating beautiful emission nebulae like the Orion Nebula or the Eagle Nebula. The radiation and stellar winds from these massive stars also compress nearby gas clouds, triggering new waves of star formation. In this way, one generation of stars can give birth to the next, a cascade of creation spreading through the galaxy. But these massive stars also have a dark side. They live fast and die young. While a sun-like star will burn for 10 billion years, a star 100 times more massive might last only a few million. When these giants exhaust their fuel, they do not fade quietly. They explode as supernovae, some of the most energetic events in the universe. The explosion releases as much energy in a few weeks as the star emitted over its entire lifetime. It creates a blast wave that tears through the surrounding space at a significant fraction of the speed of light. Any planets nearby are sterilized or destroyed. Even planets many light years away can be irradiated by the supernova's gamma rays and cosmic rays. Yet even in destruction, there is creation. The supernova disperses heavy elements throughout the galaxy, enriching the interstellar medium with carbon, nitrogen, oxygen, iron, and all the other elements needed for rocky planets and life. Without supernovae, the universe would contain only hydrogen and helium. There would be no solid surfaces to stand on, no water to drink, no air to breathe. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created in the heart of massive stars and dispersed by supernova explosions. We are, quite literally, made from the ashes of dead stars. And those ashes are now being incorporated into new stars and planets, continuing the cycle. Our star was likely born in such a cluster, surrounded by siblings of various masses. Over the billions of years since its birth, those siblings have dispersed across the galaxy. Some might have exploded as supernovae. Others might now be red giants or white dwarfs. And some, like our star, are still burning steadily on the main sequence. We will never know which stars were our sun's siblings. They could be anywhere in the galaxy now, indistinguishable from the billions of other stars. But they share a common origin, a common birthplace in a long-vanished stellar nursery. In that sense, all the stars born in the same nebula are family, even if they never meet again. The galaxy itself is a vast stellar ecosystem. Stars form, live, and die in a continuous cycle. Gas and dust collapse to form new stars. Those stars shine for millions to trillions of years. When they die, they return much of their mass to the interstellar medium where it can form new stars. Over billions of years, the galaxy slowly becomes enriched in heavy elements. The first stars, born when the universe was young, contained almost no elements heavier than helium. But each generation of stars has increased the metallicity, creating a cosmos where planets and life are possible. We are living in a golden age, a time when the universe has just the right mix of elements to create rich planetary systems. Within this galactic ecosystem, each star plays its role. The massive stars live briefly but burn brightly, enriching the galaxy with heavy elements and triggering new star formation. The sun-like stars burn steadily for billions of years, providing stable environments for planets and potentially for life. The small red dwarfs burn slowly and efficiently, lasting for trillions of years, perhaps outliving all other types of stars. Together, they create a rich tapestry of stellar diversity, and among them, there may be stars with planets that harbor life. Civilizations looking up at their own night sky and pondering the same questions we do. Are we alone? What is our place in this vast cosmos? Where did we come from? The birth of our star was one event among countless trillions. In the observable universe, there are perhaps more stars than grains of sand on all the beaches of Earth. Each one has its own story, its own history, its own planets. Some formed billions of years ago when the universe was young. Others are forming right now, igniting for the first time in distant nebulae. And still others will form in the far future, long after our sun has died. The process we have witnessed tonight, the birth of a star, is not rare or special. It is one of the most common events in the cosmos. And yet, it is also one of the most profound, for it is the process that creates the conditions for everything else we know. Let us return now to our star, our sun, and the gift it provides. Every second, the sun converts 4 million tons of matter into energy. Most of that energy escapes into space, warming the void. But a tiny fraction, less than 1/1000th of the total output, falls upon the Earth. And that tiny fraction is everything. It drives the weather and climate. It evaporates water from the oceans, lifting it into the atmosphere where it forms clouds and falls as rain. It powers the winds and ocean currents. It warms the land and sea. And most importantly, it powers photosynthesis, the process by which plants convert sunlight into chemical energy. All the food we eat, all the oxygen we breathe, all the fossil fuels we burn ultimately derive from sunlight. Think about what this means. The energy that powers your body, that allows you to move and think and read these words, came from the sun. It was captured by plants through photosynthesis, stored in sugars and starches, and then released when you digested those plants or animals that ate those plants. Trace that energy back further. It originated in nuclear fusion reactions in the sun's core. Hydrogen atoms fused into helium, releasing gamma rays that slowly worked their way to the surface, emerged as visible light, traveled across 150 million kilometers of empty space, fell upon a leaf, was absorbed by chlorophyll, and through a complex biochemical process was stored in a glucose molecule. And now that energy is powering your brain. The light we receive from the sun left its surface about 8 minutes ago. But the energy in that light was created in the core millions of years earlier. A single photon born in a fusion reaction spends between 10,000 and 100,000 years bouncing around inside the sun, gradually working its way from the core to the surface. Once it reaches the surface, it escapes and makes the journey to Earth in just 8 minutes. When you feel the warmth of sunlight on your face, you are feeling energy that was created before human civilization began, energy that has been slowly percolating through the sun's interior all this time and has only now reached you. The sun also provides us with something less tangible but equally important. It gives us a sense of time and rhythm. The daily cycle of day and night governs the behavior of nearly every organism on Earth. Plants open their leaves and flowers in response to sunlight. Animals are active during the day or night depending on their adaptations. And humans have built entire civilizations around the sun's apparent motion across the sky. We measure time in days and years, both defined by the Earth's relationship to the sun. Our calendars, our festivals, our sense of the seasons, all are tied to the predictable cycle of solar illumination. The sun is not just a physical object. It is a timekeeper, a regulator of life on Earth. Cultures throughout human history have worshipped the sun as a deity, and it is easy to see why. To ancient peoples, the sun was the source of all warmth and light. When it disappeared at night or during an eclipse, it brought fear. When it returned each morning, it brought relief and joy. The sun's reliability, its daily rising and setting, made it a symbol of order and constancy in an unpredictable world. And while we now understand the sun as a physical object rather than a god, we can still appreciate the truth behind those ancient myths. The sun is, in a very real sense, the giver of life. Without it, Earth would be a frozen, lifeless rock drifting through the void. But the sun's gift to Earth extends beyond just energy. The sun's magnetic field, carried by the solar wind, creates a protective bubble around the solar system called the heliosphere. This bubble shields us from most of the galactic cosmic rays that would otherwise bombard Earth. Cosmic rays are high-energy particles, mostly protons, accelerated by supernova remnants and other violent events in the galaxy. In large doses, they can damage DNA and be lethal to life. The heliosphere deflects most of these particles, allowing only a trickle to reach Earth. and Earth's own magnetic field provides an additional layer of protection. Together, the Sun and Earth create a safe haven for life in an otherwise dangerous cosmic environment. As we have seen, the birth of a star is not just an astronomical event. It is the beginning of a story that can lead to planets, to life, to consciousness, to civilizations that look up at the night sky and ask why. The star provides the energy and stability needed for that story to unfold. It creates a warm, well-lit stage on which the drama of evolution can play out. And while not every star will have planets with life, some surely do. The universe is vast, and the number of stars is immense. It seems almost certain that somewhere out there, another world orbits another sun, and on that world, beings are looking up at their sky and wondering if they are alone. And perhaps, like us, they are marveling at the process that created their star, the cosmic dance of gravity and fusion that brought light to their darkness. The sun will continue to shine for another 5 billion years, providing warmth and light to Earth and the other planets. During that time, who knows what will happen? Life on Earth will continue to evolve. Perhaps humanity will spread to other worlds, becoming a multi-planetary species. Perhaps we will develop technologies we cannot yet imagine. Or perhaps, like most species, we will eventually go extinct, leaving the Earth to be inherited by whatever comes next. But through it all, the sun will shine on, indifferent to the dramas playing out on the tiny worlds that orbit it. It is simply doing what stars do, fusing hydrogen into helium, converting mass into energy, lighting the darkness. And in doing so, it makes everything else possible. As our journey through the birth of a star comes to a close, let us step back and consider the bigger picture. What does it mean that stars form? What does it mean that we exist in a universe where gravity can compress clouds of gas until they ignite in nuclear fire? These are not just scientific questions. They are philosophical ones. The fact that the universe operates according to laws that allow for the emergence of complexity, structure, and ultimately life is itself remarkable. A universe with slightly different physical constants might have no stars at all, just an eternal fog of hydrogen. Or it might contain nothing but black holes. We live in a universe finely tuned, whether by chance or design, to produce stars and planets and us. The process of stellar birth that we have witnessed is an example of emergence, the appearance of complex phenomena from simple rules. Start with gravity and thermodynamics, add some quantum mechanics, and you get stars. Add chemistry and time, and you get planets. Add more time and the right conditions, and you get life. And eventually you get beings capable of understanding the process that created them. This is the cosmic perspective. We are not separate from the universe, observing it from outside. We are part of it, a way for the universe to know itself. Our atoms were forged in stellar cores. Our energy comes from nuclear fusion. We are, in the most literal sense, children of the stars. When you look up at the night sky and see stars, you are looking at countless ongoing stories of stellar birth, life, and death. Some of those stars are young, recently ignited, still surrounded by the disks that will form planets. Others are middle-aged, like our sun, burning steadily. Still others are elderly, swollen red giants nearing the end of their existence. And some are already dead, their light still traveling through space even though the star itself exploded long ago. The night sky is not a static backdrop. It is a dynamic tapestry, constantly changing, constantly evolving. We just live such short lives that we perceive it as unchanging. The study of stellar birth is relatively recent in human history. For most of our existence, we could only wonder how stars came to be. Ancient peoples invented myths to explain the lights in the sky. Gods, spirits, holes in the firmament through which divine light shone. It is only in the last century that we have understood stars as nuclear furnaces, Only in the last few decades that we have directly observed protoplanetary disks and planets forming in real time. We live in an extraordinary age, a time when we can witness the universe's creative processes not just with our eyes, but with telescopes that see in wavelengths invisible to us, revealing hidden wonders. Every image from a space telescope is a gift, a window into processes that took billions of years to unfold. And yet, for all we have learned, there is still so much we do not know. We do not fully understand how planets form, though we have good theories. We do not know how common life is in the universe, though we are searching. We do not know if there are forms of complexity we have not yet imagined, structures and processes that exist on scales too large or too small for us to perceive. The universe is far stranger and more wonderful than we can yet comprehend. Every answer we find leads to new questions. Every mystery we solve reveals deeper mysteries beneath. This is the joy of science, the endless frontier of discovery, the humility that comes from realizing how much remains unknown. What is the purpose of all this? Why does the universe bother to create stars and planets and life? These are questions that science cannot answer. Science tells us how things happen, not why, but perhaps the answer lies in the act of creation itself. The universe, through its laws, seems to have a tendency toward complexity. Left alone, matter does not remain simple. It organizes. It structures itself. It creates atoms, molecules, stars, planets, and eventually life and consciousness. Perhaps the universe, in some sense, wants to be interesting. Perhaps the existence of conscious beings who can appreciate and understand the cosmos is itself the point. We are the universe waking up, becoming aware of its own existence, marveling at its own beauty. This perspective can be both humbling and empowering. Humbling because we are so small, so brief, so insignificant in the grand scheme of things. A single human life spans perhaps 80 years. The human species has existed for perhaps 300,000 years. The sun will shine for 10 billion years. The universe is already almost 14 billion years old and may continue for trillions more. We are a fleeting moment in cosmic time, and yet empowering because we are here now, in this moment, able to understand these truths. We are the cosmos made conscious. In us, the universe has created beings capable of appreciating its beauty, of understanding its laws, of asking deep questions about existence. That is not insignificant. That is profound. As we conclude this segment, take a moment to absorb what we have learned. The birth of a star is a process that takes millions of years. It begins with a dark cloud and ends with a brilliant sphere of nuclear fire. It requires gravity, pressure, temperature, and time. It is governed by physical laws that apply everywhere in the universe. And it is happening right now in nebulae throughout the galaxy, in countless other galaxies throughout the observable universe. The creation of light from darkness, the emergence of order from chaos, the transformation of potential into actuality. This is the cosmic story, and we are part of it. Never forget that when you look up at the night sky, you are looking at family. Those stars are your kin. You share a common origin in the Big Bang, a common fate in the heat-death of the universe, and a common nature as temporary islands of complexity in an ocean of entropy. While we have focused on the birth of a single sun-like star, stellar birth takes many forms. Let us briefly tour some of the most spectacular stellar nurseries in our galaxy. places where stars are being born right now in vast numbers. First, the Orion Nebula, perhaps the most studied star-forming region in the sky. Located about 1,300 light-years away, it is visible to the naked eye as a fuzzy patch in the Sword of Orion. But through a telescope, it is revealed as a spectacular cloud of glowing gas, lit from within by thousands of young stars. The brightest stars, the trapezium cluster, have blown a cavity in the surrounding cloud, creating a cathedral of light in the cosmic darkness. Next, the Eagle Nebula, home to the famous Pillars of Creation. These towering columns of gas and dust are several light-years long, sculpted by the radiation from nearby massive stars. At the tips of the pillars, dense knots of material are collapsing to form new stars, even as the pillars themselves are slowly being eroded away. This is star formation in action, captured in a single iconic image. The pillars will not last forever. In a few million years, they will be entirely dispersed by the relentless onslaught of stellar radiation. But new stars will have formed from their substance, continuing the cycle of birth and death. The Carina Nebula, one of the largest star-forming regions in the galaxy, is home to some of the most massive stars known. Eta Carinae, a star system over 100 times the mass of the Sun, dominates the region. It is so massive and so luminous that it is on the verge of tearing itself apart, having undergone a massive eruption in the 19th century. The radiation and stellar winds from Eta Carinae and other massive stars have sculpted the nebula into fantastic shapes, creating pillars, bubbles, and arcs of glowing gas. This is a region in turmoil where star formation is both triggered and disrupted by the violent lives of massive stars. Not all stellar nurseries are so dramatic. Some are quiet and dark like the Taurus molecular cloud. This is a diffuse region of gas and dust about 450 light-years away, where low-mass stars like our Sun are forming slowly and steadily. There are no massive stars here to light up the nebula or blow it apart. Instead, we find dozens of young T-Tauri stars scattered throughout the cloud, each one quietly gathering mass from its surrounding disk. These are the stellar nurseries that produce the majority of stars in the galaxy, unremarkable perhaps, but essential to the cosmic ecology. One of the most spectacular sights in the sky is the Tarantula Nebula in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way. This enormous star-forming region is so bright that if it were at the same distance as the Orion Nebula, it would cast shadows on Earth. At its heart is the star cluster R136, containing some of the most massive stars ever discovered, including several with masses over 200 times that of the Sun. The radiation from these monsters ionizes the surrounding gas, creating a nebula that glows with the light of millions of suns. This is star formation on a scale hard to comprehend, a cosmic factory producing stars by the thousands. Closer to home, the Rho Ophiuchi cloud complex is one of the nearest star-forming regions, only about 400 light-years away. It is a colorful tapestry of different nebula types. Blue reflection nebulae, where starlight scatters off dust. Red emission nebulae, where hydrogen gas glows. Dark nebulae, where dust blocks background light. And embedded within this colorful chaos are dozens of young stars and protostars, each one a world unto itself. This region is a favorite target for astrophotographers because of its stunning colors and complex structures. But beyond its beauty, it is a laboratory where we can study star formation up close, resolving individual protostars and their disks. These are just a few examples from our own galaxy. But star formation is a universal process. In every galaxy we observe, we see regions where new stars are being born. In spiral galaxies like the Milky Way, star formation occurs primarily in the spiral arms, where gas is compressed as it moves through the density wave. In elliptical galaxies, star formation has largely ceased, as most of the gas has been used up or expelled. But in starburst galaxies, star formation occurs at rates hundreds of times higher than in normal galaxies, triggered by collisions or interactions with other galaxies. The universe is a dynamic place, and the birth of stars is one of its most fundamental processes. Each of these nurseries is unique, shaped by its particular history and environment. But they all follow the same basic process. Gravity compresses gas. It heats up. Photostars form. Fusion ignites. Stars are born. This is the universal story of stellar birth, playing out across the cosmos in infinite variations. And with modern telescopes, we can observe this process in unprecedented detail. The James Webb Space Telescope, in particular, is revolutionizing our understanding of star formation, seeing through the dust that obscures visible light to reveal the hidden protostars within. Each new image is a revelation, showing us details we could never see before, bringing us closer to understanding how stars and planetary systems truly come to be. As we near the end of our journey, let us look not just at the past and present of star formation, but at its future. Will stars continue to form indefinitely? Or will the universe eventually run out of raw materials? The answer depends on the fate of the universe itself, which depends on its total energy density and the nature of dark energy. In the most likely scenario, the universe will continue to expand forever, gradually cooling and becoming more diffuse. In this future, star formation will continue for trillions of years, but at an ever-decreasing rate as the available gas is used up or locked away in stars and stellar remnants. The peak of star formation in the universe actually occurred several billion years ago, when the universe was about 3 to 4 billion years old. At that time, galaxies were rich in gas and collisions were more common, triggering intense bursts of star formation. Since then, the rate has been declining as the available gas is consumed. Today, the universe forms only about 10% as many stars as it did during that peak era. And the rate will continue to decline into the future. We live in the twilight of the age of stars, well past the cosmic noon but long before the final sunset. In about 100 trillion years, the last star will form. After that, no new stars will be born. The universe will contain only the stars that already exist, slowly burning through their remaining fuel. The massive stars will have long since died in supernovae. The sun-like stars will have become white dwarfs. Only the red dwarfs, the smallest and most efficient stars, will still be burning. These tiny stars have such low luminosities that they can burn for trillions of years, far longer than the current age of the universe. The last red dwarf will not die until perhaps 10 trillion years from now, long after everything else has faded. And when it does, the age of stars will truly be over. But even after the last star dies, the universe will not be entirely dark. White dwarfs will continue to glow faintly, slowly radiating away their residual heat over countless eons. Black holes will emit Hawking radiation, though so feebly that it would take 10 to the power of 100 years for a solar mass black hole to evaporate. The universe will become a cold, dark place with only the faintest glimmers of light scattered across unimaginable distances. This is the heat death, the final fate of a universe governed by the second law of thermodynamics. Entropy always increases. Order always decays into disorder. Eventually, everything reaches the same temperature and no further change is possible. This sounds depressing, and in a sense it is. But it is also trillions upon trillions of years in the future, a span of time so vast that it is meaningless to us. The universe we live in now is young and vibrant, full of stars and galaxies, energy and light. The age of stars will last for thousands of times longer than the universe has currently existed. And during that time, countless wonders will unfold. Planets will form and evolve. Life will arise and diversify. Civilizations will rise and fall. The universe has only just begun its story, and the best chapters may still be ahead. The eventual heat death does not diminish the beauty and significance of what exists now. There is also the possibility, however remote, that our understanding of the universe is incomplete. Perhaps dark energy behaves differently than we think. Perhaps there are processes we have not yet discovered that could alter the fate of the cosmos. Science is always provisional, always open to revision in light of new evidence. What we know about the future of the universe is based on our current best theories, but those theories could be wrong or incomplete. The universe has surprised us before, revealing phenomena we never anticipated. It may surprise us again. The one thing we can be certain of is that we do not know everything. For now, we can be grateful that we exist in an era when stars still shine, when the universe is still rich and complex, when there are still mysteries to explore and wonders to discover. We are living in the golden age of the cosmos, a brief moment, cosmically speaking, when the conditions are just right for life and intelligence to emerge. Before this era, the universe was too hot and dense. After this era, it will be too cold and diffuse. We are here now, in the sweet spot, able to look up at the stars and understand what they are, how they formed, and what they mean. That is not an accident. That is a privilege. That is a privilege, and it comes with a responsibility to appreciate, to learn, to preserve, and to share. The birth of a star is the beginning of a story that can last for billions or even trillions of years. But it is also part of a larger story, the story of the universe itself. And that story includes us. We are not separate from the cosmic drama. We are participants, actors on the stage, both observers and observed. The atoms in our bodies were forged in stellar cores. The energy that powers our lives comes from fusion, reactions in the sun. The very existence of our planet depends on the precise conditions that allowed our star to form and burn steadily. We are intimately connected to the stars, not just metaphorically but physically. And that connection should inspire in us a sense of awe, a sense of gratitude, and a sense of responsibility to protect and preserve the one planet we know harbors life. As our journey through the birth of a star draws to a close, let us take a moment to reflect on what we have learned. We began with a simple question: where does light come from? And the answer, as it turns out, is both simple and profound. Light comes from stars. Stars come from clouds. Clouds come from the death of earlier stars, and the cycle continues, an endless process of creation and destruction, birth and death, light and darkness. This is the cosmic wheel, turning slowly but inexorably, driven by the fundamental forces of nature. And we, brief though our existence may be, are part of that wheel. We are made of star stuff. Looking back at the stars, trying to understand our origins, think back to where we started. Dark, cold cloud of gas, so diffuse it would be considered a vacuum on Earth. And yet from that near emptiness, gravity was able to create something extraordinary. A sphere of plasma, 1,000,000 kilometers across, burning at 15 million degrees, converting matter into energy, shining with the light of 400 trillion watts. The transformation is almost magical, except that it is not magic. It is physics. It is chemistry. It is the natural consequence of the laws that govern our universe. And that, in a way, is even more amazing. The universe does not need magic to create wonders. It creates them through the simple, patient application of natural law. Throughout this journey, we have used the language of science to describe what happens: gravitational collapse, nuclear fusion, hydrostatic equilibrium. These are precise technical terms that describe precise physical processes. But do not let the technical language obscure the fundamental beauty and mystery of what is happening. A star is born. Light emerges from darkness. Energy flows from the core to the surface and out into space. Planets form and evolve. And perhaps on some of those planets, life arises. The scientific description does not diminish the wonder. If anything, it enhances it by showing us the deep principles underlying the phenomena we observe. One of the most profound insights from our journey is the concept of deep time. The processes we have described take millions of years to unfold. 1,000,000 years is already beyond human comprehension, but stellar lifetimes are measured in billions of years. Our sun has been burning for 4.5 billion years and will continue for another 5 billion. That is more than enough time for entire species to evolve, flourish, and go extinct. It is enough time for continents to drift across the face of a planet, for oceans to appear and disappear, for atmospheres to transform. The stars provide not just light, but time, the vast stretches of time needed for complexity to emerge. Another insight is the importance of scale. We live our lives at human scales, measured in meters and kilograms and seconds. But the universe operates on scales that dwarf our everyday experience. A stellar nursery can span hundreds of light years. A single star can contain the mass of hundreds of thousands of Earths. The energy released in a supernova exceeds the total energy output of an entire galaxy. These scales are so vast that our minds struggle to grasp them. We resort to analogies and comparisons, but even those fall short. The universe is bigger, older, and stranger than we can truly comprehend. And yet, through science and imagination, we can begin to understand it. As we have seen, the birth of a star is not an isolated event. It is connected to everything else. The star forms from material enriched by earlier generations of stars. It creates heavy elements that will be dispersed when it dies. It provides the energy and stability needed for planets to form and for life to arise. It is part of a galactic ecosystem, one star among billions, each one playing its role in the grand cosmic drama. We cannot understand stars in isolation. We must see them as part of a larger system, a system that includes galaxies, dark matter, black holes, and yes, even us. We are all part of the same cosmic web, connected by gravity, by chemistry, by history. What should we take away from this journey? Perhaps the most important lesson is one of perspective. We are small, yes, but we are not insignificant. We are brief, yes, but we are not meaningless. We are part of something larger, something ancient, something beautiful. The same atoms that make up the stars make up our bodies. The same forces that govern the cosmos govern our lives. We are, quite literally, the universe experiencing itself. And that is a profound and humbling truth. When you look up at the stars, you are not looking at something separate from yourself. You are looking at your origins, your cousins, your future. The stars are not out there. They are us, and we are them. Before we close, remember this. The next time you see a star, think about the journey it has taken. Think about the millions of years of collapse and heating, the moment of ignition, the billions of years of steady burning. Think about the planets that might orbit it, the life that might exist on those planets. Think about the generations of stars that came before it, the supernovae that scattered the elements from which it formed. Think about the future, the eventual death of that star and the birth of new stars from its remains. Every star is a story, a chapter in the endless book of cosmic evolution. And you, by understanding that story, become part of it. You become a witness to creation itself. And that is a gift beyond measure. Our journey through the birth of a star has come to an end, but the cosmos continues its eternal dance of creation. From darkness comes light. From chaos comes order. From simplicity comes complexity. And from stardust comes you. The next time you feel overwhelmed by the challenges of daily life, look up. See those points of light scattered across the darkness. Each one is a sun, many with their own families of planets. And on some of those planets, perhaps beings are looking up at their own sky, wondering the same things you wonder, feeling the same sense of awe you feel. We are all connected, all part of the same cosmic story. Remember that. Carry it with you, and let the light of the stars guide you through your darkness. Until we meet again under these celestial skies, may you find peace in the knowledge that you are made of star stuff and you are home among the stars.